Having a program that draws a green triangle, it is easy to produce Vasarely-like graphics. Viktor Vasarely was a Hungarian-born painter who became famous for such geometric forms. First of all, we need to understand what we can see here. It looks like a spherical shape, but it is only a visual illusion. In fact, we can see circles of constant color piled upon each other, putting smaller circles to the top. As we go inwards, the color changes. Circles of index 0, 2, 4 and so on change their color from red to black. Circles of index 1, 3, 5 and so on have colors of dark blue to cyan. The centers of the circles start to get elevated and then return to the center of the biggest circle. Let's implement this Vasarely painting, starting with a program that can render a single green triangle. I run the program in its initial form. We can have just this green triangle. This solution follows the rules of the homework, so the framework is included. So we have the VEC2, VEC3, MED4 classes available. And in the green triangle, we rendered a single green triangle, the single field polygon. In the Vasarely, we also have field polygons approximating circles. So concerning the vertex shader developed for the rendering of a single triangle and the fragment shader basically filling up all fragments with a constant color are just fine and they don't need any modification. The GPU program and the object, we have just a single object, the circle, but it will be drawn many times, are initialized in the onInitialization function and can be used in the onDisplay function, so they are still global variables. In the onInit function, the viewport is set. We ask for a single VAO, which will be the circle, and we bind it. This VAO will contain just a single VBO storing the vertices of the circle. When the triangle was defined, we specified the 3 vertex coordinates. This is not good anymore, and the vertices should be filled up differently. So let's change its type. Vertices will be of VEC2, and let's say that we use NV number of vertices to approximate a circle, and let it be 100. So we know the size of this array is NV. The points can be specified in a for loop, so we visit all vertices. First we need the polar coordinate associated with index I. This angle will be phi, and it goes from 0 up to 2 pi. And the vertex itself can be specified with cosine and sine according to the definition of these functions. So vertex I is just the cosine of phi and the sine of phi. And in this way we are going to have a unit radius circle. This unit radius circle is copied to the GPU, so this function is good as it was. And the array will feed input register number 0, and for each vertex 2 floats are copied. This is also good. So the vertex shader and the fragment shader are compiled and linked. And when we draw it in the draw call, instead of just 3 elements, we want all elements to go through the pipeline. We know that it is NV. So let's see what we have done. This is not exactly what we wanted, but fortunately we know the reason of this unexpected result. When the triangle was rendered, we used this option of GL triangles, but in this case we have a convex polygon, which is called GL triangle fan in OpenGL. So let's try again. Yes, a nice green triangle. This is exactly what we need. We need not just a single triangle, but about 20 different triangles with different colors and different radius and even different locations. So the drawing of the circle is put into a loop. And suppose we have MC number of circles, so it is going to be a constant again. So we have 20. We visit these circles one by one in a for loop. And when we are at a particular circle, we need the location and the color and the radius, and these parameters change gradually for internal circles. So for this gradual change, we need an interpolation variable which starts at 0 at the very beginning of the process, and it will reach 1 at the end of the process. This interpolation variable is t. Yes, so with this definition, we are interpolating between 0 and 1. The radius of the circle gradually decreases from 1 to 1 divided by MC. So with this interpolation variable, we can express this as initial value multiplied by 1 minus t, and the target value at the end, which is 1 divided by MC multiplied by t. Similarly, we have to do the same for the color, but the color is a little bit more complicated because every even circle changes their color from red to black, and odd circles change their color from blue to cyan. So these two cases must be separated. Let the color be C. We separate even and odd circles. Even circles start at red and we go to black, and for odd circles we start at dark blue and go to cyan. So I copy the circle drawing into this loop. Instead of making the color always green, here we list the computed color C. Let it run. All circles are rendered with the same radius, so later circles cover the previous one, so we can enjoy just the last circle which has a cyan color. So to control the size, the transformation matrix should be changed. We apply a scaling according to the computed radius r. As far as the scaling along the z-coordinate is concerned, it doesn't make any difference since this is a two-dimensional problem. Let's see again. Yes, it's improving. However, we do not have the three-dimensional spherical effect because all circles share the same center. So the transformation should be modified further, and we should apply a translation that moves up from the beginning, and then this translation goes back to 0. So we need another variable, the translation in direction y, which is 0 at the beginning and 0 at the end. Using the interpolation variable, we need function that is 0 for 0 and also 0 for 1. The simplest function meeting this requirement is t times 1 minus t. In the transformation matrix, the translation parameters are here in the last row. The translation along x is 0, along y is the y value that has been computed, and we do not touch the position in the direction of z. And the result is like this. It's a little bit too much, so I reduce it by multiplying it by 0.8. Not bad, isn't it?